Retro Ninjas, and welcome to another awesome day of geometry and probability. Today we get to talk about theoretical probability and what exactly some of these smaller things mean for us. And so we talk about theoretical and simple probability, we're talking about experiments. An experiment's an action or trial that has varying results. So flipping a coin, rolling a die, spinning a spinner, picking marbles out of a bag. Those are trials that the results can be different each time I do it. Now, they may be the same, but that doesn't mean that it's not an experiment. What's not an experiment is flipping a two-headed coin, because no matter what happens, it's going to be heads. There is no variation in that outcome. Okay, so our possible outcome from an outcome is what can possibly occur from that experiment. So for example, if we were to roll a die, we could roll a 2. That would be the outcome of that experiment. And then our last little piece of vocabulary is sample space. And the sample space is just a set, what we've been talking about the last couple of days, of all of our possible outcomes. So if we're rolling a die, we could roll a 1, a 2, a 3, a 4, a 5, or a 6. Those are all possible outcomes when we're doing this. Now, we can use tree diagrams to find values of our sample space when there's a couple of different actions. So we're going to draw some tree diagrams, which can be a tidbit tedious, but we're going to draw our tree diagrams to determine the number of outcomes for each scenario. So if we look at number 1, we've got picking a digit 1 through 8. So I've got the possibilities of our first experiment 1 through 8. And then we're going to top a coin. So we know that when you roll a coin, or when you flip a coin, roll a coin, knucklehead. When you flip a coin, you've got 2 outcomes. You've got heads or tails. So if we get a 1, we could have a head or tails. 2, head or tails. 3, head or tails. 4, head or tails. 5, heads or tails. 6, heads or tails. 7, curves or straight lines. Just kidding, making sure you're with me. Or an 8, that is heads or tails. So at the bottom of our tree, we would see all of the possible outcomes. So our sample space is going to be anything that can happen. So we can get a 1 heads, 1 tails, 2 heads, 2 tails, 3 heads, 3 tails, 4 heads, 4 tails, 5 heads, 5 tails, 6 heads, 6 tails, 7 heads, 7 tails, 8 heads, 8 tails. Those are all of the possible outcomes, and if we were to count them up, we would know our total outcome. So if we count 1 heads, 1 tails, 2 heads, 2 tails, etc., we would get 16 possible outcomes from this experiment. And if I look at my tree diagram, I could get that on my own. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So we know that there are 16 possible outcomes from this experiment. Now, one that should hit really close to home for some of us. Randomly guessing the answers on the last 3 of a multiple choice test. When you got 4 options, A through D. So you got 3 questions. You got no idea what it could be. But if I went through, I would say I could pick A, B, C, or D for the first one. A, B, C, draw your line first. C or D for the second one. And again for the third one, A, B, C, or D. So in those 3 questions, I have all of those possibilities. So on the first question, so now when we do our sample space, the first question I could go 1A, 1B, 1C, or 1D. And the same thing for the second question, 2A, 2B, or not 2B, 2C, 2D, and then lastly, 1, oh gosh, what the Peter was that? 3A, 3B, 3C, and 3D. So there, curly brace, Sean, make a curly brace, there we go. So there are 12 possible outcomes on just 3 individual tests. And I did not even put that in the box. Did y'all see that? That was impressive. Imagine if you're guessing more than that on the possible outcomes, and there's only 3 of those that are correct. So the next one's a doozy, so I went ahead and filled it in. But you can see choosing a day of the week and then a letter from the word math. So we've got 7 days of the week, 4 letters in math, 28 possible outcomes. Now, some of us are starting to see the pattern. And mathematicians all over the planet have helped us with that pattern. They delivered us the fundamental counting principle. Now, trees can be helpful, and they can help you look and see and understand what's happening and visualize it. But sometimes you don't want to draw out 7 days of the week and then spell math 7 more times. So if we want to use the fundamental counting principle, we can multiply our 2 experiments together and find our total number of outcomes. So if our first activity can occur, and we'll label it M, number of ways, and another activity can occur in N number of ways, then that both activities can occur together in M times N number of ways. So let's go back before we even do these next ones, and let's see if we can apply the fundamental counting principle to the 3 examples we did. Well, the 2 we did together and the one I showed you. So let's go back to the first one. The picking a number 1 through 8 and tossing a coin. So there were, if we're doing fundamental counting principle, let me see if I can give us a little handy dandy box right here so we can help distinguish between what's going down. So if M represents a number 1 through 8, which would be 8 possible outcomes, and N represented heads or tails, which was 2 possible outcomes, if we just multiply 8 times 2, well, would you look at that? You get 16. Same thing for number 2 we did together. Let's make a little handy dandy extension of our outcomes box. Okay. M was 3 questions. N was 4 possible answers. So if we multiply the 2 together, we get 12. Just like the number of outcomes we got from the tree. And then this nice big long one, that would have taken up half the video time. Okay. Let's go, come on now. So we got M was the number of days in a week, which is 7. N was the number of letters in the word math, which is 4. And as you can see the pattern, 7 times 4 is 28. So the fundamental counting principle helps us by saving us a little time. So let's go ahead and do a couple of these only using the fundamental counting principle. We're not going to draw it out with the tree, okay? So month of the year, how many months in a year? 12. And then a digit 1 through 9, so that's 9 possible selections. And 12 times 9 is 108. Man, that's a little easier. Letter of the alphabet, there's 26 letters in the alphabet. And tossing a coin, 2 possible outcomes, heads or tails. That would be 52. A pair of breeches, a shirt, and a belt. When you got 3 pairs of breeches, 5 t-shirts, and 2 belts, 3 times 5 times 2 is 30. Rolling a standard die 4 times. Now we're repeating the same experiment over and over again. But the first time we roll it, there's 6 outcomes. The second time we roll it, there's 6 outcomes. The third time we roll it, there's 6 outcomes. And the last time we roll it, there's 6 outcomes. So that gives us a combination of 1,296 possible outcomes. Choosing a student from a class of 32 and then another from a class of 27. So 32 times 27. Multiply those together. I could choose students 864 different ways. Spinning the spinner on the left 3 times. Well, we got a spinner that has 16 possible outcomes on it. So the first time we spin it, we got 16 chances. The second time we spin it, there's 16 chances. And the final time we spin it, there is still 16 chances. So 4,096. Tossing a coin 5 times. So 2 times 2 times 2 times 2 times 2, or 2 to the 5th, which would be 32. Creating a 4-digit passcode from the digits 0 through 9. Now this is the funny part because people mess it up all the time. Notice the ones above it said 1 through 9, so we only had 9 digits. But when we go 0 through 9, we no longer have 9 digits. We've got 10. So 10 the first time, 10 the second time, 10 the third time, and 10 the fourth time. So 10 to the 4th power is 10,000. And lastly, choosing a perfect square that is a number less than 50, then a letter from the word signature. So perfect squares less than 50. It's kind of annoying, but there's 7 of them. All right, so we got 49, right? So if we're talking about what's in that set, 49, 36, 5 squared is 25, 4 squared is 16, 9, 4, 1, 2, 3, 4, 5, 6, and then of course 1 is a perfect square. Gotta love when they throw some actual math at y'all, huh? So 7 possible perfect squares less than 50. Then the number of letters in the word signature is 9. So we got 63 outcomes. So now we're going to go ahead and move our discussion into theoretical probability. So theoretical probability is a little different than our outcome and our experimental probability, but not that much, because it's just the probability that we're going to measure the chance of a specific event occurring. Turn my pen on. So we want the chance that a specific event is going to occur. So to do that, all of our outcomes need to be equally likely. We'll talk about it when that's different. Okay, all outcomes equally likely. We're going to determine the number of favorable outcomes, basically what we want to happen. That's our favorable, what we want. So if we go back to that outcome probability, if I want to roll a dice and I want a 1, the probability that I roll a 1 would be the outcome that I want to occur, okay? So the biggest thing, and this will follow you through all probabilities as you continue throughout your mathematical journey, probability will only be of value between 0 and 1, okay? Probability can never be greater than 100% it happens, and can never be less than 0% it happens. I know we like to live in a world of hyperbole, and I can guarantee you that 110% that's going to happen. Well, in mathematics, that just doesn't exist. Okay, so when we look at our probability, it can be expressed as a fraction. So let's say 3 out of 4. It could be expressed as a fraction, as a decimal, which would be 0.75. Or as a percentage, so 75%. None of those numbers are outside of 0 and 1. They're all between it. When we do that, that's what we're going to look for. So you'll see in our first examples, you get P, which stands for probability, and multiple of 3. So we look at our board, how many multiples of 3 exist on this spinner? So we have 3, 6, 9, 12, and 15. So that the total number of possibilities, what we want to happen if we were to flick this spinner, there are 5 favorable outcomes. Okay? And then out of those 5, we want the total number to go on the bottom, which would be 16. And if we were expressing this as a decimal, we got 0.3125. And if we want a percentage, we got 31.25%. It's that simple. How about a prime number? Prime numbers are numbers that can only be divisible by 1 in itself. On our board, there are 6 of them. Take my word for it. Okay. 6 of them, if I were expressing that in decimal form, it'd be 375. And then in percentage form, 37.5%. So we want the probability that it's even. So all the even number possibilities, let me go ahead and clean up my handy dandy wheel right here. So we've got a couple of events occurring. So we've got the probability that the number is even. So we can have 2, 4, 6, 8, 4, 5, 6. I guess I could have just divided them all by 2, huh? 7 and 8. So the probability that is even or greater than 5. So there's 8 possibilities out of 16. Now, remember that or statement. That or statement is big because if we think about set Venn diagrams, we would include everybody in both sets. So because we got an or statement, we're going to add them, and then we're going to be like, hey, let's figure it out. So greater than 5. So we got 1. We've already included 6, so we're not going to count it. We got 7, already included 8, so we're not going to count it. 9, 11, 13, and 15. What is that? 6. Okay, so there's 6 possibilities. Did I double count somebody? Oh, 1 is not, 5 is not greater than 5. You silly goose. Oh man. Why didn't y'all stop me? I know you can't stop me. You're invisible. But that's okay. I can fix it. All right. See how I noticed that I needed to have 5 at the end there? 5, 4, 3, 2, 1. So now we've got all of these. So there were 5 possible outcomes out of 16. So 8 of those are even. 5 of them are greater than 5, but do not include the ones that were already counted for even. So we're going to add them together, and we get 13 out of 16, which in decimal is 0.8125, and in percentage, 81.25. All right, and this next one is an and statement. So if or means add, and is going to mean multiply. So and we don't really need to multiply it because now we've got some restrictions that are going to make it. So we're going to our wheel here, and because they put and, we've got a lot of restrictions we get to deal with. So it needs to be odd and at most 9. So we need an odd number that is at most 9. Well, 1 satisfies that, 2, 5, 7, and then at most means it can be, so 9. So we've got a fraction, 5 out of 16, 0.3125, and 31.25%. I know, a lot of different things, but that's why we focus so much on set theory and making sure that what we were doing was correct and adding everything in there. All right, let's go. Pencil box contains 5 red, 12 blue, 10 green, and 3 yellow markers. So we got 5 red markers, 12 blue markers, 10 green markers, and 3 yellow for a total of 30 markers in the box. Okay, if a marker is chosen at random, what is the probability that's not yellow? So we're going to take everybody that's not yellow, which includes 27 markers. 27 out of 30. And of course, if that fraction can reduce, we're going to math frac it. Now, number 10. Probability that a drawing of an ace or a diamond from a standard deck of cards. Guys, decks of cards are going to be common. Get used to some of our relationships. Like there's 52 cards in the deck. 26 of those are red. 26 of those are black. So 26 red, 26 black. You've got 13, and we're in the red. So you got 13 diamonds. 13 hearts, 13 clubs, and 13 spades. And then each of those sets, you've got 1 through 10, Jack, Queen, King, and Ace. And then these guys are considered face cards. I know, it's a lot, but get used to your guys. All right, so an ace. How many aces in our deck? We got 1 in each suit, so 4 out of 52. How many diamonds in our deck? There are 13 diamonds in our deck. But we double counted somebody because we have already the ace of diamonds in this one. So we're going to subtract that guy. Now, 4 plus 13 is 17, minus 1 is 16 out of 52, which reduces to 4 out of 13. Guys, we're going to get a lot of practice on these ones because these are a lot of your SAT. All right, now they're going to take our Venn diagrams and they're going to go ahead and have us dissect some Venn diagrams. So first off, students in homeroom were asked if they have a part-time job and if they have their driver's license. The results shown are in the Venn diagram to the left. If a student homeroom was chosen at random, find the probability. Simplest form. So first off, how many total students were surveyed? 4 and 8 is 12, plus 6 is 18, plus 7 is 25. That's our total sample size. So how many people had a part-time job? So we got 8 plus 6, because remember, it's everybody in that circle over 25, which is 14 over 25. No driver's license. So we're going to go ahead and say they only have a part-time job they're included, and the 4 people that don't have either. So that's 12 over 25. Part-time job and driver's license, that's our intersection, so 6 out of 25. Part-time job or a driver's license, that's our union, so that's everybody that has both of them. So you would say 8 plus 6 plus 7 over 25. So was that 14, 21 out of 25? I guess I could have just subtracted 4, huh? How about driver's license and no part-time job? So only a driver's license will be those 7 individuals. Mom and dad's taking care of them, I guess. Okay. The complement of an event, so something that's not going to happen. So this is why I wanted to skip that Finn question, and I wanted to come back. So the complement of events, part of an event, is not going to occur. Okay, it is not going to happen. Since the sum of all probabilities in a sample space is 1, we want to find the probability of it not occurring. So 1 minus, because this is our total probability, 1 minus the probability of the event occurring. Probability that it will not rain tomorrow, the probability that it is going to rain is 11 out of 15. It must be baseball season. What is the probability that it's not going to rain? Well, you could be like, Coach, I know if it's 11 out of 15, it's going to rain. But if it's not going to rain, I can just subtract from 4. But that's all we're doing here. So the full probability would be an 15 out of 15. That minus 11 out of 15. And guys, I use 15 out of 15 because that's just 1. And I just didn't want to have to do double math. Or you can just pop it in your El Calculador and it'll kick it out for you. 1 through 30 selected at random. Probability that it's not a multiple of 4. Okay, so first off, the probability of even getting a multiple of 4 is 7 out of 30. Okay, so you got 4, 8, 12, 16, 20, 25, 28, 7 times. Yep. So we want 30 out of a 30 that it's going to happen faux show. But we want what's not happening is we're not rolling a multiple of 4. So that's how we get 23 out of 30. Experimental probability is the probability that repeated trials are going to occur. So we're going to flick this thing 50 times, and then we're going to just document the data as we're rolling, okay? So find the theoretical and experimental probability. If it's spun, again, so we're saying, hey, we flipped this thing 50 times, right? That's in our experimental probability. If we're just speaking simply theoretical, one outcome, if I were to flick this guy, the probability of getting an orange would be 1 out of 5. If I were to just flick that knob. But from our experiment, well, we saw that 12 times it landed on orange, and that was out of 50, and we'll reduce that 6 out of 25. And the numbers are close, but they're not exact because variations do occur. How about red or green? So that would be 2 out of 5, because it can be either or. That would be our theoretical. One time that happens. But if I look at red, I had 5 out of 50. If I look at green, I had 10 out of 50. Put them together, we get 15 out of 50, which is 3 out of 10. And our last problem, not purple. So we want, so that could be any of the other 4 colors. Okay, so now we can add up all the colors, not purple. Or, so we got 50 out of 50, right? Minus 7 out of 50. I can use that last thing we did, and it gives us 43 out of 50. All right, guys, that sums up our lesson for today. Go be great.